Is my slide visible to all?
Yes, sir.
Okay. So please make your mic mute. So today we will see the chapter 4, fundamentals property relation and calculations. I hope so. We have gone through the available lecture on SWIM portal. So we will see on the some concepts on the thermodynamic property and their relationships, and based on that we will solve the some problems. Then we will see the some Clapeyron equation for the two-piece systems, then Clausius Clapeyron equation, and based on that problem. So first we will see the classification of thermodynamic properties. So there are the three types of properties: reference properties, energy properties, and derived properties. In a reference property, these properties are used to define the state of the systems, such as temperature, pressure, volume, and entropy. And energy properties: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. So these four properties, and here energy property and enthalpy we studied in previous sessions. So we will study uh, Helmholtz free energy and Gibbs free energy in these sessions. So derived properties are these property partial derivatives of energy properties and reference properties, such as specific heat, coefficient of expansions, Joule-Thomson coefficient, and coefficient of compressibility. So first we see the free energy. So free energy measure the system's ability to do the work, right? Here is a heat engines, which is a QC, right? QH. So here is a Q quantity of heat absorbed by the systems, like QH. Then here is a work done, and some energy transferred to the low temperature reservoirs. So TS means unavailable heat of doing useful work. So this terms is a TS, right? This is a work. The Q minus TS, that is a free energy at a different condition, like constant volume and constant pressure. When constant volume, that's called the Helmholtz free energy, and at constant pressure, Gibbs free energy. I hope you all of you understand. At a particular specified conditions, means constant volume and constant pressure. Understood or not?
Yes, sir.
Yes, okay. Now Helmholtz free energy, that is also called as a work functions. So how it is? So it is a thermodynamic potential that measures the useful work obtainable from the closed thermodynamic system at the constant temperature and the volume. So Helmholtz free energy denoted by the A, which is equal to U minus Ts, right? So at a constant temperatures, means isothermal conditions, one minute. When we change from the state 1 to state 2 at a constant temperatures, so A is equal to U minus T, is right. So you can write down these terms like d is equal to dq by t. So you can write down by U minus Q. All right. So based on the first law of thermodynamics, yeah, right. So it means it get cancels. 1 minute. Here is a only QR. So del E is equal to minus W door. So let's call the work functions. So here U and T and S are the means is a state function. So A is also a state function, and internal energy and entropy are the both the extensive. So A is also extensive property. Similarly, the Gibbs free energy. It is thermodynamic potentials that measure the useful work obtainable from the closed thermodynamic system at a constant temperature and pressures. So here H and T is also state function, so G is also a state function, and here H and S are the both extensive, so G is also the extensive property. So W, when we put the derive this equation, you get so this denoted by the network. Right. Now coming to the relationship among the thermodynamic properties. So first we see the exact differential equation. So Z is equal to function of x and f. So when differentiate dz, so dz by dx y dx plus dz divided by dy is equal to x. So here m this is denoted by m and this by m. Now you can write down dm divided by dy at a constant x, which equal to the dn divided by dx y. So this exact differential equation will helpful to solve to understand the relation between the thermodynamic property. So here are the fundamental properties: internal energy, enthalpy, Helmholtz free energy, Gibbs free energy. So d is equal to T minus ds P dV, then dH TdS plus VdP, like U plus PV. You put the U value here and you get the TdS plus VdP. Then d is equal to minus PdV minus HdT. So similarly put the all the relation in the starting expression, like A is equal to U minus Ts, you will get this. Similarly it is equal to, right, you will get this. So these are the thermodynamic property. So to understand this thermodynamic property with each others using the Maxwell equation. So here Maxwell equation are helpful to in replacing unmeasurable quantities appearing in a thermodynamic equation by the measurable quantities, right. So this is the mnemonic diagram for the thermodynamic property relations. So at the corner are the reference properties like temperature, pressure, volume and entropy, and side are the energy properties like internal, then the Helmholtz free energy, Gibbs free energy and enthalpy. So here if the arrow of this upward line, that is cross line, is pointing towards the side variable, then it is taken with a negative sign. So it means that this side negative, and if the arrow of the line is pointing away from the side variable, then it taken is a positive this side. So how it is? First we see the internal energy. du is equal to u. So here yes, here is a means positive signs. TDS. T ds, and here is PdV. Here is the negative sign. This side the positive ones. Similarly, DAH. Can someone try based on this arrow DH? So both will be the positive. T ds plus V dp. I hope you understand. dA P dV minus S dt, and dg, here T and S, so here is a T negative, so S dt, here is positive signs. Right. TDS plus VDP, then minus SDT minus PDV, then minus DT VDP. All of you getting or not?
Yes, sir.
Now use the exact differential equations. So for that, dt divided by dv at constant entropy equal to minus signs dp divided by ds at constant value, right? This one, this one. This is the relationship for the based on the internal energy. Similarly, this is based on the entropy. This is based on the like dt dp and this is based on the g, right? If you remember from this diagram, you can develop this equation based on that. You can easily make these relations. So now we'll see some problems based on the thermodynamic properties and Maxwell equations. So starting from the one, the three identical closed systems of pure gas are taken from an initial temperature and pressures T1 P1 to the final state T2 P2. Each by the different path. Which of the following is always true for the three systems? So delta represents the change between the initial and final state. U, S, G, Q, L, W are internal energy, entropy, Gibbs free energy, heat added and work done respectively. The options are given. Can anybody tell the answer to this one?
Sure, wait for 1 minute.
Sorry. Yes. Q and W are the path function. Here is a three system.
The option would be there.
B.
Yes.
No, wrong thus. Because here is a means work done is a path functions. So it would not be the same, it would be the difference. Like A systems, B system, C systems. So here Q and W are the different due to the these are depend on the path. So here internal energy, entropy and Gibbs free energy are the state function. So there is a means delta G, delta U and delta are the sims.
So whether B option correct or D?
D is D. Because it will be the change. Here is a work done. So what would change with the path?
Yes.
So here the option are the D. Now question 2. The Maxwell relations derived from the differential expression for the Helmholtz free energy dA is. Can tell the answer someone? Option are here.
So D option.
D 1 minute. D dp by dt v is equal to ds, right? D is equal to minus pdv minus dt, right? So dp by dt ds by dv, right? Now which one of the following is correct for an ideal gas in a closed systems? Option are given. I'll have to try to solve and tell the answer. For ideal gas, PV is equal to RT, right? So here option VR, PR, VR, PR. So from the fundamentals properties, DH is equal to TDS plus VDP and DU TDS PD. Yeah, please make your mic mute.
Sir, option number है.
Sorry,
Option number है.
Oh, no, this is the wrong. Let's try to in another way.
The other options are not matching.
1 minute. These equations taking the partial derivative dH by dP at a constant enthalpy. So which is equal to V. And du ds at constant value, right? So we have to put this value in these equations, means V value here and T value here. So dH by dP, yes, equal to P, or du upon ds V. Getting or not this one? You can put the means different value, means you can take the partial derivative with respect to the different properties at a constant, means different constant properties, and I try to put.
Yes, option D is correct.
Option D is correct, right?
Please explain one. I am not getting.
So here property dH is equal to TdS plus VdP. Now take a partial derivative with dP at constant entropy, right? So dH by dP is equal to, so here is a constant, it get cancels. So here only 1 minute VdP. Only here only getting the only V. And for the d is equal to TdS minus PdV, take a partial derivative with the ds at constant value, right? D is equal to Ts at constant value, so it get cancels at a constant value. So here is only Td, right? Now put this value in the ideal gas equations.
Okay, sir.
Okay, good. Now question for a pure substance, a Maxwell relation obtained from the fundamental property relation du is equal to TdS minus PdV. It is simple ones. Here is option. Tell someone.
Sir, option
Sorry.
option A.
Yeah. Right. Now question 5, here is a statement. If volume, internal energy, entropy and G represent the respectively the molar volume, molar internal energy, molar entropy and molar Gibbs free energy, then match the entry in the left and right columns below and choose the correct option. All of you try to solve and tell the answer. Here is a in group 1 given du by dv and dg by dp, means dg. So how to start from the internal energy functions, internal energy and the Gibbs free energy, sorry, Gibbs free energy expression.
Option A option.
All right. So from the fundamentals, energy relations, du is equal to TDS minus PdV, right? And dg is equal to V dP minus SDT. So now take a partial derivative with respect to here is a group 1 given based on that. So plus du by ds at a constant value is equal to T, right? And du divided by dV at a constant entropy minus P, right? Similarly for dg, so here P du by dV at constant entropy pressures, this ones, and du divided by ds at constant volume temperatures, this one. Yes, one. All of you getting or not?
Yes.
Yes, sir.
All the question based on the which was asked in the gate, so I am solving that ones. So question 6, an ideal gas at a temperature T1 and pressure P1 is compressed isothermally to pressure P2 greater than P1 in a closed system. Which one of the following is a true for internal energy U and the Gibbs free energy G of the gas at the two states? Here are the two states given, T1 and P1 is compressed isothermally. So option are here given. Here is a isothermal compress, so it means temperature constant. So temperature in constant means generally internal energy depend on the temperature. So from state 1 to state 2, so internal energy should be same due to the isothermal conditions, right? U1 is equal to U2. Now calculate for the G1. So this will not. So Gibbs free energy dg is equal to V dP minus SDT, right? So here is isothermal condition, so dt, this term should be 0, right? Now an ideal gas, so put V is equal to RT by P here and integrate this. ln is P2, 1 minute. When you integrate delta G is equal to RT ln P2 divided by P1, right?
Sir, B option.
B right. So here as I mentioned that P2 is greater than P1. So here, so the P2 greater than P1, so delta G is positive. So G should be greater than G1, right? This one. All of you understood?
Yes, sir.
Here are the Maxwell relation questions here. Maxwell relation corresponding to the identity d is equal to TdS plus VdP plus summation ui dni is. I think here is here ni indicate the compositions. Can anybody tell the answer this one? Yes, here is add means one terms this summation ui plus dni. So yeah, ui you can write down. So dh dn. Here is
Sir,
yes.
D option.
1 minute. B T N I 1 minute. DT no. So use the exact differential equation. So dt by dp at constant entropy and composition, right? dv by ds at constant p and ni, right? Yes, np and ng. Understood or not?
Yes.
Okay.
So what is mu I and I in this equation?
Sir, here is a NI means composition. Now UI denoted by here is a UI is equal to partial DH divided by DNI with the constant S N P and NJ, right? This is. And I think next session we will say based on this like excess properties and so on. Here is the Ni is a composition, like you can say mole fraction, mass fraction and so on. Now also hint entropy heat capacity relationships. When you derived, so you get ds by dt p is equal to cp dt and ds by dt at constant value cv t. So 1 minute. You can write CQ dt, right? Du by dt. One minute, Cp by ct. So your dq, you can write down tds dt, it cancels, cp by t 1, sorry cp ds by dt. 1 minute, I am getting confusion here. Okay. So based on the some Maxwell relations, we get these terms. So ds by dt at a constant pressure, which is equal to cp by t, and ds by dt at a constant value is equal to cv by t. So we can write down cp is equal to dq by dt, right, and cv is equal to dq by dt v. Now put the value dq is equal to t ds here also. So put the here t ds by dt at constant pressure. So ds by dt p is equal to cp by dt. Similarly, we put this expression in this relations, you get ds by dt at constant value cv by dt. Now some differential equation for the entropy. So here AC is equal to means entropy equal to the function of pressure and temperature. Then derive you with generate the expression, then you will get ds is equal to cp divided by dt minus du by dt p dp. Similarly for the entropy is a function of volume and temperature, so this relation you will get. Similarly for volume is a function of pressure and temperature, derive the equation like here. d by dp at constant value dp plus d by ds dt at constant pressure dt, right. Now here ds by dp, right, ds by dt p, so you can put this value, this ones in this expression, then you will get this like. Now in this terms use this relationship means Maxwell relations shape, then you will get these terms. Similar like the others expression like this one and this, you will get.
Sir, how the second expression is coming in DS equation?
Second one, second one.
Yes,
Okay.
yes.
So yeah, entropy is a function of volume and temperatures. So ds is equal to ds by dv, right, at a constant temperature, dv plus ds divided by dt at constant value dt, right. Now we have ds divided by dt, right, at constant value, which is equal to cv by t, cv by t dt, right. Now ds by dv t, so 1 minute. Now one ds by v t, dv, sorry, ds by dv dv dt, which is equal to dp by dtv. 1 minute. Right.
Okay, sir.
Getting or not these terms?
Yes, sir.
Okay. Now we will see the sums on one numerical ones. So here is a statement: air expand steadily through a turbine from 6 bar 800 Kelvin to 1 bar and 520 Kelvin. During the expansion, heat transfer from air to surrounding at 200 Kelvin is 10 kilojoule per kg air. Neglect the change in kinetic and potential energy and evaluate the irreversibility per kg of air. So assume air to behave as an ideal gas with Cp equal to the 1 kilojoule per kg into Kelvin and R 0.3 kilojoule per kg into Kelvin. So we have to calculate the irreversibility. So how to calculate, tell someone. So how to check the irreversibility of the systems?
Sir, it is
Sir,
expanding.
if entropy decreases,
Now from which terms you denote it? Means we have to calculate something like some based on the properties or so which property indicate the irreversibility?
Volume.
Yeah, right. But there is a one energy property, is entropy, right? Right. So when any process possible, so delta S total greater than or equal to the 0 for any possible process. Right. So when delta S total equal to the 0 for reversible process. And delta S total greater than 0 for the irreversible process. Right. Right. So we have to calculate the total change of entropy, right? Getting or not point?
Yes.
Okay, so allow me try to calculate the entropy. So it should be the greater than 1. So here we have to derive some equations. So here entropy is a function of the temperature and pressures, like S is equal to function of temperature and pressures. Now differentiate ds by dt at constant ds by dp t dp, right? Now we can write down ds divided by dt at constant pressure cp by t, just we derive in last slides, right? 1 minute. Now based on the relations of Maxwell from the Maxwell's, so ds by dp t which equal to the minus dv by dt p dv, right? Now from ideal gas PV is equal to RT. PV is equal to RT. So here we have to make this ideal gas into these forms. So dV by dt at constants, 1 minute, sorry 1 minute, V is equal to RT by P. Now differentiate with the temperatures at constant at a constant pressure. Right? Now put this value in this expression, so which is equal to ds cp t dt minus r by p into dp, right? Now integrate these expressions from state 1 to the states 2. So Cp ln T2 minus T1. In the equation given the temperature and pressures, means the initial state and final state, Rp into ln P2 divided by P1, right? So put the value until the answer delta is
0.106 kilojoule.
yeah, right, good,
Kelvin.
kilojoule per kg into Kelvin. Here is the first part. So here is a mention that the heat transfer from air to the surrounding, right? So here is a heat transfer is a 10 kilojoule per kg here. So now
Here, that we are getting total change in entropy
yeah, yeah,
or for the system.
yeah. Now but here is a mentions heat transfer from air to the surrounding at 300 Kelvin is 10 kilojoule per kg air. So based on that we have corresponding entropy you have to calculate, right? So based on this condition, so I think I denoted the corresponding entropy. So which is equal to dq by t, right? So from air to surrounding means air is the system. So from heat transfer from air to the surrounding. So here is the negative signs. So minus 10 divided by 300 Kelvin. So which is equal to minus 0.0033 kilo kg Kelvin, right? Now we have to calculate total entropy change, means delta S total. Add this one and this one 0.107 minus 0.033. So which is equal to 0.
0.1037.
0.074, right?
Yes, yes.
74 unit is a kilojoule per kg, kilojoule kg into Kelvin, right? So here is the ask evaluate the irreversibility per kg of air. So irreversibility of per kg of air is equal to 0.074 kg per kilojoule per kg, sorry, kilojoule per Kelvin. That is the irreversibility. And it is a positive, means greater than the 0 for the irreversible process. All of you getting or not? Means you can write down irreversibility.
Yes.
Okay. Now question 9, on a TS diagram, the slope of constant volume line for an ideal gas is. Here is the option given: less than that of constant pressure line, more than that of constant pressure line, less than the constant enthalpy line, and equal to that of a constant enthalpy line. I'll have to try to solve this one on the TS diagram. The slope of the constant volume line. So here is the TS diagram, means dt by ds, right, at a constant volume lines. Similarly, m is equal to, right, this is also based on the derive based problem. So considering here entropy is a function of temperature and volume. You can write APR of TV, right? Now differentiate ds by ds by dt v dt plus ds by dv t dv, right. We know the internal energy relationship TdS minus PdV. Now differentiate with the dt at constant value, so you get t. One minute. ds by dt at constant value. So ds by dt v 1 by t du by dt v. Right. Similarly, VDP plus TDS. VDP plus TDS. So we just derive, so we will get the ds by dt at constant pressures Cp by T. Now put this ds by dt. 1 minute. Sorry. So you can write down this ones. Du by dt is equal to C v by t, and similarly for ds dy by dt p is equal to Cp by t. For ideal gas, Cp greater than Cv, right. So here Cp is equal to ds by dt p greater than Cv, dt get cancels, ds by dt v. But here ask the dt divided by ds at constant value. So here dt divided by ds column at a constant value greater than dt get, right. So here is a dt by ds at constant volume greater than the pressure, constant pressure line.
So is there any approach by making the graph or by the equation we have to solve?
1 minute. Now here we So based on only the expression we can say that. Right. So this is not a useful movement. Much force. So when we add from the internet energy, you get the du by dt v is equal to t ds divided by dt v. Then ds by dt is equal to 1 by t. So du divided by dt we can write down this is cv. So cv t. Similarly from enthalpy get the ds by dt p equal to cp by dt. Now for ideal gas cp greater than cv for a gas and cp which is equal to the cv at for a liquid. So based on that we can reason that. So initially the ds by dt p greater than the ds divided by dt v, but here ask dt divided by ds. So when exchange with dt divided by ds v greater than dt divided by ds at constant pressure lines. I hope
Okay.
okay. Now for two-phase systems, so here are the Clapeyron equation dP divided by dt which is equal to delta H and d delta V. Here is delta is a change in enthalpy and delta V change in volume, it is temperature with pressure. So for classes Clapeyron equations, the volume of the liquid is small in comparison. Here is the assumptions. Volume of the liquid is small in comparison with the volume of vapors. Right. So here when you put delta V Vg, right, here is the assumptions. Now you from ideal gas Vg is equal to RT by P, put this in the equation and integrate, then you will get this relations to solve the two-phase systems. So based on that Clapeyron and classes Clapeyron equations, so questions number 10, to obtain the integrated form of classes Clapeyron equations. So here is the expression ln p2 by p1 is equal to delta H r into 1 by t1 and t2. From the exact Clapeyron equation, it is assumed that
A option.
here d1 because vapor phase BV as an ideal gas and heat of vaporization is independent of temperature. So option A is D, right?
Yes, yes.
Okay.
You.
Now question number 11, at 100 degrees Celsius, water and methyl cyclohexane both have a vapor pressures of 1 atm. Also at 100 degrees Celsius, the latent heat of vaporization of these compound are 40.63 kilojoule per mole for a water and 13.55 kilojoule per mole for the methyl cyclohexane. The vapor pressure of water at 150 degrees Celsius is 4.69 atms and at 150 degrees Celsius the vapor pressure of methyl cyclohexane will be expected to. Here are the options. I'll have to try to solve using Clapeyron equations. dP by dt directly proportional to T. So it is the same temperature difference. So dP is directly proportional to the delta H, right?
I think sir it is less than K of
Yeah, right, right, right. Here, here is a means delta P means directly proportional to the delta H. So here at 150 degree Celsius, pressure is 4.69 atm. Initially, the latent heat given at 100 degree Celsius 41.63 kilojoule more, right, which is greater than the methyl cyclohexane. So it should be greater than so should be less than the 4.61, right. All of you getting or not?
yes sir.
Question 12. For a pure liquid, the rate of change of vapor pressure with the temperature is zero point 0.1 bar per Kelvin in the temperatures range of 300 to 350 Kelvin. If the boiling point of the liquid at 2 bar is 320 Kelvin, the temperature in Kelvin at which it will be boiled at a 1 bar up to 1 decimal place each. I have to calculate the temperatures which boil at a 1 bar. So in this questions given dP by dt 0.1 bar per Kelvin. Can someone tell how to solve to calculate the temperature at which boil at a 1 bar? Here is a given bar 1 bar 3 to yes.
Is not given, so we can after integrate we find the P2 and
Just a simple one dP by dt. We can write down P2 minus P1, right, and T2 minus T1. So this is given. So you put the value here P2 here is a 1 bar and 2 and 2 to given 320, right. Sorry, T2 here is a green 320 0.1 minus 1 here is a 2 minus 320. I'll have to try to and solve.
310
Sorry,
310
310, right. So 31 Kelvin temperature required boil at 1 bar.
Sir, here the temperature range is 300 to 350.
Yes, right.
Actually, I that it is T1 and T2, but actually T1 is giving us 320.
No, here is given the some rate of change of vapor pressure with temperature 0.1 bar Kelvin in the temperature range for this range. But here is a mention that the boiling point of liquid at 2 bar is 320 Kelvin. So we have to calculate temperature at a 1 bar. So this rate in between this ones. So here is a 3 1 and here is a 320. So both are temperature in between 300 to 350 Kelvin, right?
Okay.
So question 13, the vapor pressure of water is given by in P sat equal to A minus 5000 by T, where A is a constant. P sat is a vapor pressure in ATM and T is a temperature in Kelvin. The vapor pressure of water in ATM at 50 degrees Celsius approximately. So I'll have to try to solve and tell the answer. How would we solve? Means we have to calculate the vapor pressure at 50 degrees Celsius. And here is a relation given. Can someone tell how would you solve this?
Sir, is value of A is given or not? Without value of A,
Yeah, you're right. You are right. But you know the some concepts when water means water boil at 100 degrees Celsius, right? So what would be the pressure at 100 degrees Celsius?
it is 1 atm.
Right. Now, so 100 degrees Celsius is equal to 373 Kelvin, right? So at this temperature, pressure is Psat is equal to 1 atm. Now, put this temperatures and pressure in this equation, then you will get the A value, right?
Okay, sir.
13.405. Now simple one. Now convert this 50 degrees Celsius into Kelvin and put the A value here, then you will get the Psat. Mm, 13.40.
It is somewhat negative, minus 1.07, which is wrong.
Negative.
I think calculation mistake.
Yes, right. Calculate here. 1 minute. P 13.405 minus
Yes, sir, it is coming good.
323. Sorry. Here is some mistakes. Here is a ln PSAT. Please check it. This is a ln.
Okay.
(323 Kelvin). So P sat is equal to 8 something.
So it is about 0.125.
Right. So here is the option D, right? Because
Yes, yes.
yes, right. All of you got clear?
Yes.
Now question number 14. 1 kg of saturated steam at 100 degrees Celsius and pressure 1.01325 bar is contained in a rigid wall vessel. It has a volume 1.673 meter cube. It cools to 98 degrees Celsius. The saturation pressure is 0.943 bar. And 1 kg of water vapor under this condition has a volume 1.789 meter cube. Now the amount of water vapor condensed in kg. All of you read carefully and try to solve. Equal to the 98 degrees Celsius, right? So here initial condition is vapors, like one value 1.673 meter cube and 100 degrees Celsius. It get condensed. Initially vapors and final vapor plus condensate. Right, value 1.73 meter cube and 90 degrees Celsius. Here is the mention 1.78 meter cube of saturated vapor at 98 degrees Celsius, 1 kg. 78 meter cube. At 98 degrees Celsius, 1 kg. And similarly for 1.673 meter cube, vapor at 98 degrees Celsius. So here is the cross multiplications. So 1.673 into 1 divided by 1.789, right? So this is a 0.935 kg. So the amount of water vapor condense. So water condense 1 kg 0.935, 0.065, right? I hope all of you get understood.
Okay, sir. Okay, sir.
Okay, right. Now same questions, but here so statement same, but here we have to calculate latent heat of condensation in kilojoule per kg under this condition is. So here temperature given, means temperature initial temperature, final temperature given T1 T2, pressure also given. So how would you calculate latent heat of condensation? Can someone tell how would it how would it solve? So based on the Clausius-Clapeyron equations, ln P to sat divided by P1 sat,
Is equal to del H by R
right?
bracket में 1 upon T1 minus 1 upon T2.
Now put the value all here and tell the sum and answer. Zero point nine. To 8.31. Three 73 minus 371. 371.
So it is approx 540.
5
40.
540 kilojoule per kg.
Yes.
No, I think this is I think wrong.
ओए यहाँ पे ये इसकी वैल्यू क्या डालनी है? ओए आर की वैल्यू क्या डालनी है?
8.314.
क्या दिया है? यूनिट क्या है? प्रेशर का यूनिट टेम्परेचर।
बाहर है वो तो एलएन में है ना।
अच्छा तो आर की वैल्यू डालेगा तो यार 0.3
0.3 रुक जा एलएन 0.943 डिवाइड बाय 1.01325 क्या वैल्यू होती है पता ना आर की इसमें
Divided by
81314 किलो जूल पर मोल है क्या जूल पर मोल तो नहीं
अगर 8.3 नहीं आएगा मिस्टेक कर दिया
रुक 8.3
1.0325 divided by answer. 521, right? 521. It is making some mistake.
सर ये ऑप्शन
Sorry. Check it. Option C. One minute. Here is a mention that ये you have to divide by 8.314 divide by 18. Right. So here ln 0.943 1.0325 into gamma. So here 8.31. So unit kilojoule
it is 4
mole Kelvin. So 8.314 divided by 18 molecular weight of the waters into 1 by T1 means 373 371, right? Now calculate 96.3 kilojoule per kg.
सी ऑप्शन सर
Right. All of you got this one?
yes sir
Okay, so I cover all the questions based on the chapter 4, thermodynamic properties and their relations, and two page based on the two page. So if you have any doubt, please ask.
sir can we get the pdf of these questions that you have practiced in the last session
Yes, I already share on Google Drive.
okay in the post you have shared
Okay. No,
and
And on a SWAYAM portal, you will get some Google Drive link. Then you can open. You can download the questions.
Okay. Okay. Also, recently there's one exam is conducted on 28th and 29 April. So, what will be the pattern? Objective type, or we have to have?
Mostly the objective one. Objective means we have to solve, we have to derive some equation and we have to solve it. Just you have to put the some value.
ठीक, okay.
Okay. Okay. Thank you.
Thank you, Dr.
Thank you.